Hey guys, welcome back to Introduction to Computer Networks at NTU. This is now week 14, episode 25, which means we're very close to summer, right? So this is in fact the second last lecture. Second last week of lectures, all right? And hi, Ting Qi and Bo Yu. Good afternoon to you all. For this week, we do have quite a few assignments. One is PA9. This is the last one in the whole series. If you manage to complete PA7 and 8, PA9 shouldn't be much a problem. Okay, you just need to make your web server secure. And then, hey guys, it does look like that we have many quizzes this week. But no worries. The first 4 quizzes we'll be going through today, they are straightforward and in a series to try to make a point, try to give you some intuition how distance vector, the second routing protocol works. Okay, and the last 4 are further to allow you to exercise the distance vector routing algorithm you've learned. All right. Good. And hey guys, I'm sorry to make you anxious a little. Exam 3 is coming up 2 weeks from now. But given how you guys did for exam 1 and 2, I think you guys will do fine. Okay? And the topics today are, let's wrap up link state routing, and then we'll start distance vector routing. And in fact, the reason that we want to have distance vector is because there's something not so good about link state, all right? If you recall from last week, link state routing works this way. Given the network topology, we apply the Dijkstra algorithm, recall? The computation complexity is n squared and potentially optimizable to n log n. Okay. And in the end, we derive the forwarding table, what we are looking for inside the router. Okay. But the thing is this, okay? Applying Dijkstra algorithm means that you need to have the network topology. So this network topology here seems to be a give-me. But you see, the internet is a distributed system, right? A router is a router. How does the router know what the internet's topology is? Wow, that is a little bit far-fetched, isn't it? Okay, in link state routing protocol, there's a part of the mechanism that defines how a router discovers the network topology. Okay, and that is what the first video is about. It's a little bit long, 4.5 minutes, but it's very important that you know. And the very first part of the video is just to give you a quick review of link state, and then you will see that mechanism propagating this thing called the link state report. Link state report. So again, 4.5 minutes. Let's see if you can follow. To put simply, link state routing works this way. Each router implements the routing algorithm. It's going to wait until the total information of the network is in place. Then it calls the Dijkstra algorithm. At the end of the calculation, we get the least cost path from this router to every destination possible in the world. So that is essentially the shortest path tree. Now that router being the root of the shortest path tree, we'll see there are multiple branches out to the rest of the world. Taking one branch, it gives you the shortest path to a certain set of destinations, another branch to another set of destinations, yet another branch to yet another set of destinations. And so from the tree structure, okay, we can construct the forwarding table, and that is how the forwarding table is calculated in the control plane. Next is just to install it into the data plane. Now, the only part I'm going really quick without mentioning much is this: how we get the total network information so we could apply the Dijkstra algorithm in the first place. That is done through this link state broadcast. Each node, okay, in the network is going to generate link state report based on very local information. That includes the ID of the node itself, the ID of the immediate neighbors, and the cost, okay, on the link to these immediate neighbors. Okay, so these are the local information. Node, the neighboring nodes, and the link cost to the neighboring nodes. So all of these local information is going to be in the link state report coming from the node. This link state report is going to be broadcasted, meaning, okay, going out through the entire network, being received by all other nodes. So all nodes eventually will receive link state reports from every other node. Okay. And these link state reports from every other nodes, including the node's local information, is going to be used to restore, okay, the total network. Let me give you an example to illustrate how that is done. We have a very simple network here, only 4 nodes. Okay, you see, U connects to V, U connects to W, U connects to X. Okay, so if we are node U, okay, and generating node U's link state report, it's going to contain this: the ID of the node itself. Yeah, there are 3 neighboring nodes, V, W, X, and the cost on the link to these nodes, 5, 3, 7. So U to V, link cost 5. U to W, link cost 3. U to X, link cost 7. Similarly, V is going to generate its link state report, which is going to contain only 1 entry. It connects to U, link cost 5. The link state report from W should look like this: 2 neighbors, U and X, cost being 3 and 2. Link state report from X is contained 2 entries, U and W, link cost 7 and 2. So each of these nodes, U, V, W, X, is going to broadcast their link state report, and every node in the network is going to receive its own local information and every other node's link state report. Therefore, node U here is going to receive the link state reports from V, W, and X, which we know already look like this. The way to restore the network topology is this. Okay, node U knows the local information. It connects to V, it connects to W, it connects to X. Cost is 5, 3, 7. Now, seeing node V's link state report knows that V and U is connected, cost is 5. V, U, I'm U, so I know, okay, and the cost is 5. W's report is going to tell, okay, the cost to U is 3, which you already know. Oh, W is also connected to X with link cost 2. So W connect to X, link cost 2. X report says I connect to U, so X connect to U, you already know. X reports also that it's connecting to W, link cost 2, which you already have. And you now manage to reconstruct the total network information from receiving link state reports from all the nodes in the network. And it's contributing also so that other nodes receiving U's link state reports can also reconstruct the total network. So you see this one here, U connecting to VWX. Yeah, isomorphic, okay, of the network there. All right, so we have this link state report broadcast that's going on across the entire network. And that is why it's called the broadcast. So you can imagine, right, the amount of traffic, okay, required to send these link state reports around will be high. And each router will need to keep this network information, right? If the network is as big as the internet, okay, you see potentially issues doing link state routing, and it's probably not possible to run link state throughout the internet. So that was the last piece of the puzzle, link state routing. Other problems you see here. Now you know a little bit about the link state broadcast. Yeah, some of you might see this. These link state broadcasts, it's going to travel the entire network. And it's coming from every router, right? So you have n copies of these packets going to n nodes. The bandwidth consumption is again at this scale. And to store the topology information in the router, right? So we discussed the complexity of Dijkstra algorithm. We only talk about the time complexity. We have not yet talked about the space complexity. It's also huge, right? In the worst case, you have n nodes fully connected to every other node. Then you have what? N square number of links. You need to store costs, okay, for all these links. Ugh. Not very scalable when the network goes big, when n goes large. And yeah, that is exactly why we want distance vector. So on the internet, we run this other routing protocol called distance vector. Okay, so here's the video to kind of introduce distance vector, but in a way that let me motivate you why distance vector and talk about the general idea of distance vector. So it's a little bit more like how human beings pass rumors. Okay, I pass the information I know to you, and you pass the information to others. Okay, and of course, before you pass on further, you kind of aggregate what you see with what I see. Yeah, very much like the human rumor network, distance vector routing. And guys, right after this video, which is very brief, about 1.5 minutes, we will have a series of quizzes coming, 41 to 44. All right, and probably be taking the fast responders for bonus for all these 4 quizzes. All right, good. So short video, 1.5 minutes, and 41 coming right up. So you see, link state routing works fairly well for small networks where n is small. For access network, institutional network, local area network, it might be okay. But for the entire internet's backbone, there's no way we use link state routing. And that takes us to the second routing algorithm, distance vector in the chapter. So distance vector routing is exactly here to address the space complexity, to address the message exchange complexity in link state routing. If you think about it, the reason that the link state routing takes so much space, requires sending of so many messages, is because in order for the extra algorithm to run, we need the total network information. So the question to ask is this: can we come up with a path? Can we discover best paths, best routes without knowing the global information? You know what? It's possible. We just need to be a bit patient though. Okay? So Polly here might have 2 neighbors, Alice and Bob. Bob and Alice do not know each other. Okay, there's no path existing from Bob to Alice. But if Polly shares how Polly knows Alice to Bob, then Bob will know that there's one way, right, to reach Alice, which is through Polly. Okay, so I tell my neighbors, and you tell yours, okay, about what you know. Gradually, okay, the network, okay, will spread the good news out and discovering a path, a route, okay, to every other node in the network. That is the general idea of distance vector. Oh, right, and that takes us to quiz 41. And let me try to draw here. Yeah, so this is quiz 41. All right, so what you are asked to do is to role play a router. So you are router X right here. All right, and you want to send messages to a router that's far away here, W. Okay, and you have 2 neighbors, router Y and router Z. All right, and you know the link cost from U to Y and from U to Z. So you know the cost, 9 and 4 here. Good. Now recall the principle. I tell my neighbors, neighbors tell the neighbors. So you as one of the routers on the network, you get also information from your neighbors. So router Y, router Z tells you these. Router Y says, I know a way to W. And Z says, I have no idea where W is. Okay, so would you pass the data to Y or Z? So pick one of the neighbors to do the forwarding and tell, more importantly, why. All right? Yeah, this one is very straightforward. I see you guys already. Yeah. Say something already. Okay, that's great. So for the rest of you, feel free to type. And again, although I'm taking the first responders for bonus, again, I will try to also take the responders within a certain time window, okay, for bonus. All right. So how about 1 minute? So guys, keep on typing. All right, so it's obvious, isn't it? Y at least knows the way. I would like to pass to Y because it guarantees some information, so it is fine for me. Well, for Y's case, the cost is something limited, but for Z, hey, the cost can be, yeah, infinite. So definitely Y over Z, right? So no, this one seems gimme. Yeah. Now, guys, come back here. Let's move on to 42. Okay. Again, the same setting. You are still router Y, sorry. And you still want to send data to W. But this time, neighbor Y says, I know a way to W, and the path cost from me to W is 3. And Z says, okay, now I know better. Okay, this time I know a way to W, but the path cost is 10. Okay, now you being X, which one would you choose to forward the data? Okay, and more importantly, why? All right, let's go to the score space and channel 42. Yeah, I see some of you have already started work. Yeah, you've already posted your answer. So, but it's okay. Take your time. Type it up. Let's give it again 1 minute. All right, guys. You guys will work fine as routers, right? So, for example, I see Jordan here. So the explanation is very clear, right? So Jordan there calculated the overall cost to reach W. And that will be either going through Y, the cost will be 9 plus 3, right? Because the path cost was 3. And plus the link cost together 12, which is lower than the sum of the link cost to Z's pass to W, Z's best pass to W. All right, so you do the calculation. Yeah, so hey, many of you are very fast, and many of you can be fast and elaborate exactly, okay, how you do the calculation. Very good. All right, now let's move on. And by the way, before you go, yeah, quiz 42 essentially tells how distance vector works. Okay, from all these reports from the neighbors, from the information from the neighbors, you pick the best from what you see across what you know and what your neighbors know. All right, now let's move on to quiz 43. All right. So you see the scenario is pretty much the same. You're still router X, you still want to send data to W, okay? And you have two neighbors, except that this time, you see a little bit more information. Hey, there's a link between Y and Z, and hey, the link cost is 2. But you see, router Y and router Z is still telling you this information that you hear from, just like in quiz 42. Right? So in this case, would you pass the data to Y and Z, or Z, I'm sorry, okay? And Y, all right? So in this case, would you send the data to Y or Z, all right? So let's go to the score space and channel quiz 43. All right. I suppose that some of you might come up with something slightly different for different reasons. Let's see what they will be. But for many of you are still typing or thinking, take your time. I think this one is a little bit tricky. Feel free to take your own stand. Be unique. Okay, so the bonus will also go to those who have a unique idea. Okay, you just need to justify why you think this way. Okay, so this one, let's give it a little bit longer time. How about 3 minutes? Okay. Interesting. All right, guys. Yeah, as I said, I thought that some of you might choose to answer the question differently. Okay, I guess for many of you, the obvious one is this. Okay, send the data to Z, and then have Z send it to Y, and then Y send it to W. Together, the total cost is only 9, which is better than 12, better than 14. Okay. Which was told by the by the neighbors. Okay, so if you follow this advice, right, follow this information, you pass it through Y, which is 12. If you pass it through Z, this will be 14, right? But if we know that there's a link cost between Z, Y being 2, right? As human beings, having a global picture, yeah, we thought that we pass it to Z and somehow designate Z, send it to Y, and then on. But the thing is that, hey, Z probably doesn't know, right? Otherwise, Z won't be saying that the cost to W is 10. So I see that for many of you, especially those that are really, really quick, yeah, we as human beings, we see the entire topology information, except all those in the dotted lines. Okay, otherwise, right, we know better. There's a route X, Z, Y, W. But you see, in distance vector, it's just neighbor telling neighbor. So the end result will be more like what, let me go back to the score space. End result will be more like what Yu Zheng, Team 16 is saying. Yeah, pass it to Y. But this is pass it to Y based on the information from Y and Z. Okay, although they both know how to walk, Y's path costs less. Can only see my neighbor exactly. Yeah, the cost is only this. Okay, So Yu Zheng here is playing the role of a distance vector router. Okay, the rest of you are actually more intelligent. Okay, a router having more information. Okay, so let's see. Yeah, I see more of you saying that, hey, why not just do X, Z, Y, and W? But what is going on here? If Z, Y, W can be 2 plus 3, 5, why does Z tell X the cos is 10? Why? All right. Yeah, so first characteristic of distance vector is this. You make a decision based on the information you collect from the neighbors. Okay, so you don't really know that there's a link cos between y, z that is 2. Okay, but if there is such a short link cos, such a like link cos link between y and z, right? Z should be reporting something better. And why? Because, hey, as a human rumor network works, there's actually a delay propagating the information, propagating the latest information, and that is why. Okay, and so this next video, okay, is to summarize quiz 41 to 42, because what we are doing before quiz 43 is that among the options, which is informed by the neighbors, which one is the best, and that is pretty much the calculation the distance vector routing protocol is doing. All right, so the spirit of distance vector routing. This video is very short, I think just 1 minute. Okay, and but right after that, we'll take another quiz 44. In 44, you will see what's going on with quiz 43. Okay, it will take some time, take more observation before you converge to the best routes, particularly in distance vector. That should give you a rough sense how a router discovers a route without seeing the entire network topology. Yeah, that is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be x, and the cost from the neighbor to destination y. You can calculate the sum of x and y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, x and y for that particular neighbor. So you pick I such that xi plus yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hop that leads to the shortest path to the destination. Alright, so from this video you can see that the distance vector routing, the computation part is essentially going through all the neighbors and calculate the sum of the link cost plus the shortest path from the neighbor to the destination. And among all these neighbors, which neighbor offers the smallest amount, the lowest path from you to the destination. Alright? And now we move on to quiz 44. All right, so this is the quiz called perspective and perception. All right, so what you're seeing in the middle as human beings, right? This is a elephant, okay? But you see, elephant is huge, okay? So on this picture, we have 6 scientists, okay? And each of them, right, are blindfolded. Okay, so they can only depend on the sense of touch. Okay, so you see that the scientist at the top here, okay, touching the ear, thought that, hey, yeah, it's thin and soft, okay, flappy, so it's a fin. And so, for example, this scientist in the middle on a letter touching the trunk of the elephant. Hey, it's solid, right? And big and wide. It's like a wall. So each of these scientists, based on their perspective, they only perceive a part of the elephant. Okay, it would take some time for these scientists to exchange how they perceive what this object they are experiencing is about, in order to finally get this is perhaps an elephant. Okay, so as a router on the internet, there's only the router's perspective, and as a router on the internet, the perspective determines how you perceive what is the best route. All right, so now let's exercise, okay, and try to guess this object behind the question mark. All right, and Polly has invited a few users, okay, testers, to try to experience this object behind the question mark. So the first tester says this: oh, it's a drink. The second tester also tried and say, hey, it's cold. And then the third and the fourth and the fifth tester says, it's sweet, it's soft, and it's chewy, right? So gradually, you get more information, and you probably know better what it is. And guys, for this one, hey! Yeah, okay, you happen to have a drink there, okay, and it's cold. It does look like it's cold. Let's see what's on the label. Oh, okay. Oh, and this is in Chinese. Allow Polly to translate. It's boba. Okay, I think it's a green tea boba. Okay. All right, very good example there. Okay, so guys, hey. Yeah, boba. So, but boba is probably not the only, possibility, isn't it? Yeah. So, guys, what it is? Okay, let's go. Hey, let's allow 1 minute. Okay. Okay, very specific, very articulate. Good. Okay, bubble. All right. All right. Yeah, I think you guys got it. Okay, some would actually say, so Polly is, what Polly had in mind is bubble tea. But you see that some of you say a little bit more generally, cold drink with chewy toppings. Yeah. Bubble tea, a drink with, ai yu jelly. All right. Annabelle, all right. Okay, you're a professional tea drinker, I guess. Yeah. So by the way, Taiwan is very well known for having all kinds of toppings in the cold beverages. Okay. 鲜草蜜. Okay. Yeah. So this is also chewy, isn't it? All right. Cool. Oh, okay. Polly is a little bit thirsty. Yeah, all right. Jelly drinks. Okay, cola with jelly inside. Interesting. I've never drank cola with jelly inside. Hey, Yuzhen, could you tell me which of the drink stores offer cola with jelly inside, or you made it yourself? That would be super interesting. Okay, it might go popular. Something very unique. Mango pudding. All right. Oh, okay. Yeah, that's a little bit mouth-watering. Okay. Yeah, so guys, given more information, you gradually know better. Okay, that's the idea of distance vector. All right, and let's move on. Let's introduce the distance vector algorithm. And I'm going to introduce the whole algorithm in two parts. Okay, the first part is about this calculation, going through all neighbors and calculating what is the best path, what is the minimum cost going through a particular neighbor, and pick the one with the minimum overall path. Okay, and there's that equation there. Okay, taking the minimum of all possibilities is called the Bellman-4 equation. And you see right on the slide that what I was describing is exactly how distance vector algorithm works. So we define the term here. dxy is the cost, okay, of the shortest path to go from x to y. And so what we're calculating here is the minimum cost to go from x to y, or to discover the shortest path from x to y. The way to do it is to go over all the v's. Okay, v's are the neighbors of the source. For each v, we calculate the cost to go from the source to the neighbor plus the cost from the neighbor to the destination. So the sum here is the cost to go from the source to the destination through a particular neighbor v. So all we need to do is just to go over all the neighbors and calculate the sum for each neighbor and pick the neighbor that gives us the minimum value. And that minimum value is the minimum cost, okay, from x to y. And that v there is the next hop along the shortest path to the destination. So by doing this calculation here, we discover the shortest path. We discover the minimum cost. And this equation here is better known as the Bellman-4 equation, because this algorithm implemented in distance vector routing is devised by these two great guys. Let's try to exercise the Bellman-4 equation using an example. And let's calculate the shortest path from U to Z. The first thing to do is, hey, we need to have the neighbors, right, reporting, okay, how they know about the destination. So use neighbor including V, W, and X. So V will need to report the distance from V to Z, and that is the entry here. X will have to report the shortest distance from X to Z. Same for W to report the shortest distance from W to Z. And then we can begin, okay, doing the calculation. So we'll be going through all three neighbors one by one. So let's take the first neighbor V. Okay, so link cost from the source to V is 2. And dVz is 5. So we have 2 plus 5 here. Okay. From U to Z through V, the cost is 7. Second neighbor, X. So this is the second one. Link cost, okay, from the source to X, 1. And dxz reported as 3. So this is 4 here. Wow, nice. Third neighbor, W. Link cost is 5. And dwz, 3. So together, 8. So obviously, 4 is the minimum value. This is the minimum cost from U to Z. And you know what? X is the neighbor that gives you the minimum cost. Therefore, X is the next hop leading to the shortest path. So here, X here, achieving the minimum is the next hop in the shortest path. And that is also, okay, the link pointing to X is the link interface to insert in the forwarding table for destination Z. All right, so Bellman-4 is the main calculation that's being done there in a distance vector router. But see, the distance vector router needs to get the other neighbors, right, as distance vector information in order to calculate, okay, the best for the router itself. So the whole distance vector algorithm is in fact an infinite loop of 3 steps. First, wait for distance vectors from neighbors. And upon receiving one distance vector, the router applies the Bellman-4 equation and find out whether there's actually a better neighbor to pass the data to the destination. And this will be done for each of the possible destinations around, right? That forms the distance vector. And the final step is this. How does your neighbor discover if there are better routes if you discover a better route, right? So when the distance vector has a change, the router will need to also propagate the information further. So send the distance vector to the neighbors. That's step 3. Okay, take a distance vector from neighbor, apply Bellman-Ford, and send the new distance vector further on. Okay, and if the distance vector doesn't change, then there's no forwarding of the distance vectors to the neighbors because there's no better information to tell. Okay, so infinite loops of 3 steps. Okay, this is the overall routing algorithm of distance vector. So that was the Bellman-Ford equation, which captures nicely how one discovers the shortest path, the minimum cost to go from the source to the destination. But you see also in the previous example, right? Calculation of the Bellman-Ford is actually based on these information, Cij, okay, the link cost from the source to each of the neighbors, and these, the shortest distance from each of the neighbors to the final destination. All right. That is also saying the distance vector algorithm as a whole contains the Bellman-Ford algorithm, but before the Bellman-Ford can be calculated, each node will also need to collect these information. Now, this is actually configured in from the network admin when the network is established. Now, this actually relies on the neighbors, okay, sending their routing information to the node. Okay, so next, what I'll be talking about is to go over the entire distance vector routing algorithm, covering both the message passing part as well as the Bellman-Ford part. Now, before I talk about the entire distance vector routing algorithm, let me introduce just one more notation. dxy is the shortest distance from x to y. This is not new. The new one is here. A node is going to maintain the shortest distance from itself to every possible destination existing in the network. So capital N here is the set of the nodes in the network. So we do have multiple values of these dxy, okay, because there are multiple values of these y's. So each of these values is the distance, the shortest distance to a destination in the network. Therefore, we call this a distance vector. It's denoted as capital D. Okay? Now, because this is the distance vector for node x, therefore it's called the dx. Good. So the distance vector routing algorithm, the goal is to derive dx, okay, for each node x. Right? And before we could calculate dx, okay, the node here needs to have 2 pieces of information. Okay, according to the Bellman-Ford equation, we need to know the link cost from the node to each of the neighbors, so CXVs. Now, in order to have the shortest distance from each of the neighbors to a particular destination, yes, we need to also know, okay, the neighbors' distance vectors. So for each v, node x here also maintain dv. And now the algorithm of distance vector routing. You see here, the key idea is it works in 2 phases. First of all, each node sends its own distance vector to the neighbors. So this is the message passing phase. And then 2. When the node receives the distance vectors from all the neighbors, Bellman-Ford equation calculation begins. And as a result, okay, the node x there discover its own distance vector. And we could loop back. Okay, this node here then will pass the dx to the neighbors. Okay, that is the general idea of distance vector routing algorithm. The Bellman-Ford equation, now this is the Bellman-Ford equation. Okay, know that when x receives all these dv's from the neighbors, okay, dx is not just one value to one particular destination. So this Bellman-Ford equation is going to be called, again, these many times, so that we derive the shortest distance to each of the possible destinations in the network, n. Final note here. Under minor natural condition, the shortest distance from x to y, at the beginning, it might be really, really bad. Okay? But as time goes by, it's going to converge to the actual least cost. So Minor natural conditions means that, yeah, for normal internet operation, this is going to hold true. To be more precise, this is distance vector routing algorithm, and it's depicted such that it looks like it's working in cycles. So each router in the network operates such a cycle. First, it's going to wait for one of these two events. Very common is that you receive a distance vector from the neighbor. Occasionally, this router here might detect there's a link cost change among these links to the neighboring routers, because these two events might affect the result of the Bellman-4 calculation. So when these two events occur, we trigger Bellman-4 calculation to begin. As a result, we get a new distance vector. Now, if the distance to any of the destination has changed, that means better route discovered, shorter distance discovered. Then we tell to the neighbors, because the neighbors might also benefit from the good news, benefit from the discovery. Right? So you see, distance vector routing algorithm working this way, it's iterative, meaning it works in cycle. In each cycle, it can all be triggered by two kinds of events: link cost change and DV update messages arriving at the router. It's also distributed because one can calculate and discover a better route and pass it to another node. So each node notifies the neighbors of a better route, and the neighbors then calculates even better route and notifies the neighbors. So in the end, they converge to the shortest path, but the effort is actually shared, distributed, and contributed by all the routers in the network. Alright, so now you see better how distance vector works, right? Then you can recall right when we begin to introduce the two kinds of routing algorithms. Distance vector is iterative, asynchronous, and entirely distributed. So that we can get away without storing the information of the whole internet. All right. And you know what, guys? Hey, some of you are actually also paying attention to the chat box. So there's a pop-up quiz, guys. Go to the chat box. Let's take the same poll we have done before we know exactly how link state and distance vector work. Do you like link state or distance vector better now? Now you know both algorithms. All right. So yeah, I see some of you are. Yeah, I see more coming in. And this time, hey, last time we have like 6 to 11, link state 6 and distance vector 11. And back then, people like link state seemingly because it's simple, right? And this time, hey, distance vector seems to win over, all the link state people. Yeah. Good. So, hey, given how we explain distance vector, it sounds also simple, isn't it? And it's very efficient. And if you don't mind waiting some time, eventually you get to discover what is the best route to go. That seems to be true. Sorry, I probably burst my mic. But no, wait until tomorrow. All right, so there's actually a very interesting characteristic in distance vector called bad news travels slow. Guys, I probably will take the poll one more time after we finish introducing this bad news travels slow characteristic in distance vector. And we'll see whether we have some of you leaning again back to link state routing. All right? All right, so you know what? That is all the time we have. We have only 2 minutes left. The next topic is to give you a full example of doing distance vector routing. And you see that this is a distributed algorithm. It's usually harder to do calculation to show example in a distributed algorithm. So that's actually start from the very beginning of the example from tomorrow. So tomorrow, very much like today, there'll be a series of these quizzes, but they are really there to help you understand, a seemingly not so friendly protocol, in an easy way. All right, so come tomorrow, follow through the quizzes, and I'm pretty sure you'll do fine in the exam. All right. Good. So with that said, that's all for today. I see you tomorrow. Okay, bye. 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 Oh, 汤圆. Oh, okay.